Okay, so let's get started with the today's session. So today's session is actually week 7, and we are into week 7 of the fundamentals of the nano and quantum photonics course. And this course is being offered on NPTEL portal by Professor Naresh K. Imani. And I'm Shazan Bhatt, and I'm a direct PhD student at IIT Bombay and Technical University of Berlin. And Uh, in the last session, I remember there was some issue with the audio, so I will try to go to that particular session to the PDF which I had uploaded, and I'll try to just briefly, I should say, uh, recap some of the important concepts which we had studied in that previous session. So, if you remember, we studied about the electromagnetic waves behavior in the two-dimensional periodic potential. And we studied about the electric and magnetic metamaterials, but unfortunately, due to some audio issue, I guess only the text was visible, although there was a lot of, I should say, information I tried to give in that particular session, but unfortunately, I wasn't able to record the audio in that particular session. So I'll try to briefly, I should say, recapitulate what we had studied. So for half an hour, I'll try to just recap for half an hour about whatever the important things I had actually talked about in that particular session. So the first of all, we talked about what is a metamaterial in that particular session, and we said that metamaterial is something which is beyond nature. It's not a material which is produced by the nature, but it's something which is artificially produced using the laws of physics, obviously. And we studied about this particular picture, which is a particular diagram, which basically shows different regions of the. It is basically a figure of between a permeability on one axis and permittivity, electrical permittivity on the another axis. So you see that if you have, let's say, for example, if you have both the permittivity and the permeability as positive numbers, then you have the case of the dielectrics where the electromagnetic waves behaves like a propagating wave. And when we talk about propagating wave, we talk about the Poynting vector, that means the flow of the energy, and the wave vector, that means the direction of the propagation of the electromagnetic wave. They are both in the same direction. So that is the obvious electromagnetic wave we know about. But if we talk about the second quadrant, which is this particular quadrant where the permittivity and permeability are, the permittivity is negative and the permeability is positive, then this is the case of the metals and some doped semiconductors, which almost behave like the metals, which are highly doped semiconductors. And in there, we have something called as evanescent waves. Evanescent waves are the decaying part of the electromagnetic waves, and they exist in these particular media. And then we define something called a skin depth, which is the depth up to which the electromagnetic wave penetrates to 1 by E of the initial value. Okay. Then the interesting case happens when you have the permittivity as negative and the permeability as negative. Both are negative. What is going to happen in that case is that you have something called as negative index materials. And the interesting part of these materials is that the wave vector and the Poynting vector, they are in the opposite direction. They are anti-parallel to each other. So that means if the wave vector or the electromagnetic wave is going in this direction, the Poynting vector is pointing in the opposite direction. So that's what makes them interesting, and that's what makes them worth studying, because it's a different phenomena which we have not seen at all. I should say, in all of the normal materials we talked about. And then we have the magnetic plasma, which we are not mostly going to deal with in this particular course, where the permeability is negative and the permittivity is positive. And you talked about some magnetic plasma or the magnetic resonances and the magnetic confinement structures and all of that phenomena related to the magnetism. So that's not what we are mostly going to mainly going to deal about in this particular section. Then here we talked about why these particular metamaterials are important. They are important because you can develop certain applications like cloaking, invisible surfaces. You can guide these electromagnetic waves using certain guiding structures. And one of the applications is in defense, where people want to, I should say, cloak or make the aircraft invisible as possible to the incoming radar signals. So if you can do that, then pretty much you can just escape the enemy aircraft and enemy radar systems, and that is beneficial from different perspectives. Whatever you may say, it can be beneficial for defense, commercial, surveillance or whatever the government is going to use it for. Okay, so then we talked about briefly about this. You might have seen that we talked about how we are going to make these metamaterials. We try to mimic the nature, and how we are going to mimic the nature by using the rules of the nature. Just like nature provides us the crystalline structures with the some repetitive arrangement of the atoms, so we are going to do the similar thing here, but we are going to create artificial periodicity with the help of some artificial made materials. Just like if you periodically arrange these nanorods, where this is the top view and this is the front view of those nanorods, you can get a different, altogether different phenomena when the electromagnetic wave interacts with these particular systems. Now, we have been talking about in this course that what happens when a wave hits up some periodic structure, the periodicity comes in, and then you talk about the phases of those particular waves, whether it's an electron in a crystalline solid or whether it's an electromagnetic wave in a periodic system where there is a refractive index periodicity or even the atomic periodicity. Okay, then we talked about a classical case wherein we know that if you have a, let's say, a rod and you dip it inside of water, because of the variation in the refractive index and because of the phenomenon of refraction, the rod appears to be bended. But that is the case in case of a normal, if you have a positive refractive index. But what happens if the refractive index becomes negative? Then what happens is basically the bend appears in the opposite direction, and that is what happens in basically if the refractive index goes into the negative regime, and your theta, which is the theta r, which is this theta angle of refraction, compared to that of this theta, they are going to be opposite. That means you will be having a opposite bending in case of negative refraction and negative index particularly. And you can simply compute it using the Snell's law, which is basically the angle of refraction using the Snell's law can be computed by negative of n2 over n1 into the sine of angle of incidence. So then we talked about briefly about tangential component, the conservation of the tangential component of the electromagnetic wave. And then here we talked about, in this particular section, we talked about why we are considering the refractive index to be negative. If both the permittivity and permeability are negative, then overall we should consider it to be positive, because negative times negative will be positive. But we forget about this plus minus sign, which comes when you just square, when you just bring the square root on both of the sides, you have the plus minus sign which comes into picture. And then we gave a simple argument that if you have this, if you for example have this positive sign, then you have the material with the gain, which is mostly used for amplification purpose. And if you choose the negative sign, you have the material with the loss, which is the only possibility that can happen, because you cannot have the gain without the I should say active material. So for example, this particular case or the gain case is only possible with the active materials. If you have active materials. So what are those active materials? These are certain materials wherein if you feed in the electromagnetic wave due to some phenomena which we are going to talk about today in today's session, that means week 7. But these active materials are like they are going to amplify these particular electromagnetic waves, just like the electronic amplification happens. And now, if we talk about again here, we talked about what is the role played by the, let's say, the dimensions of the system, which is, let's say, A, which is the periodicity of these artificially created systems. Let's say, for example, these are nanorods, and they are having certain periodicity. Then you can compare that periodicity with that of the comparison of the wavelength of the light. Okay, so then we say that if the periodicity or if the repetition is of the order of the wavelength, then you have those effects of diffraction and interference taking into place. And you talk about photonic band gaps particularly, and we have talked about it in the previous sessions. And if you have the A much greater than that of the lambda, then you talk about the geometric optics. You have to talk about the reflection, refraction, and all of those things which you have been talked about in classical optics. And but the phenomena that if you have the sizes of the much less or less than the wavelength of the light, then you have the systems of metamaterials. Then you go into the effective index method, wherein you treat this whole repetitive arrangement as a material with a single index that you call as effective index. We have talked about it briefly in the previous session. So this is the particular slide which basically explained that particular system. Then here we went into explaining how the metallic nanowire array is going to behave if you have a, let's say, if you have an arrangement of the nanowires, which are just like repetitive arrangement of the metallic nanosystems, then how are they going to behave, and what are the how the resonances is going to occur in these systems. Then you talk here we talked about basically that when the electromagnetic wave interacts with, let's say, a nanosphere, then it's going to induce certain polarized charges, which are basically these induced charges. And there is certain self-inductance also associated with these metallic systems, which is basically which basically affects the motion of the electrons in these particular metallic systems. And here, then you talked about something called as effective. There's something called as effective charge density, which basically depends upon the charge density into the fill factor. And fill factor is basically how much area of that particular nanorod is occupying over the complete area of that, let's say, particular substrate or a square. So that is the particular fill factor which we talked about. And if we do certain adjustments and include the effect of self-inductance in the effective mass, okay, and then use that effective mass in the Drude model, then we can apply the Drude model in this particular scenario also. And as per the Drude model, you get the effective index, effective permittivity to be approximately equivalent to this, and you get the effective, the plasma frequency of these particular systems to be inversely proportional to ln of A divided by R, where R is the radius of this particular nanorod, radius, and A is the arrangement or the distance between these two nanorods, or what you call as a periodicity. Then we talked about that if you have a planar metallic dielectric system, earlier this was only for the metallic system, this is only for the metallic systems, metallic nanorods. Then we went into what happens if you have a repetitive arrangement of layers of metal and dielectric, metal and dielectric. Here, let's say, for example, you talk about this Ag is a metal, this silicon dioxide is a dielectric, and you have these arrangements. Now here you talk about something called as the parallel component of the permittivity and the perpendicular component of the permittivity. And you find that the parallel component to be equivalent to the weighted average and the perpendicular component to be equivalent to the harmonic mean of these particular permittivities, where epsilon 1 and epsilon 2 are the permittivity of the medium 1 and permittivity of medium 2 respectively. And that is what basically is shown here in this on this side. This is the proof of that particular section shown. And we talked about that in actual sense, these permittivities and permeabilities, these are actually tensors because they are different in going to be different in different directions. So then you have to use the tensor notation in order to understand what is basically happening in these particular planar metal dielectric composites. And then we talk about how to get a magnetic response. How to get it? You just need a circulating currents in order for that to couple with the incoming magnetic field of the electromagnetic wave. So in order to get the magnetic response, you need a circulating currents for the magnetic field for coupling to the magnetic field component of the magnetic field of the electromagnetic field. And you know that if you have, let's say, for example, a disk, metallic disk, if it's placed in, let's say, a magnetic field of B, and the magnetic field is coming out of the plane, then the induced current will be such that it will try to oppose the magnetic field. That is as per the Lenz's law, you know it. And then there will be currents induced in that particular system. Now, what happens if you just take a part of this disk and form it into a ring? Then this induced current will again be produced or induced in this particular system, and you will be having a certain response where the electromagnetic wave will couple to the to this particular ring, let's say. But that will be a non-resonant response. Why? Because you only have, let's say, a inductive type of response in this particular system. You don't have a capacitance as such. And for the resonance to happen, you need to have both L and C in order to have the LC coupling, LC resonance, LC type of resonance. That means in the resonance, there should be transfer of energy from one capacitive element to the inductive element, and this should go on. That is what basically happens in the resonance. Okay. And that's why you need to have a capacitive type of system also in these particular arrangements. So what you do is that you split the ring. That is what you call a split ring type of split ring. I should say, just give me a moment. Okay, just give me a moment. Okay, sorry for the interruption. Just So what we say is that there should be a capacitance created. So we go to the split ring configuration where in the separation of the charges creates the capacitance. And because of this separation, there is a basically a displacement current flowing through this particular section. Okay, so I hope it is visible. Yeah, okay. So you define the capacitance, you have the inductance, then you have the resonance frequency, which depends upon the capacitance, which depends upon the, let's say, now again, if you talk about double split ring resonator, you put in another ring inside a ring, and you have the capacitance, and which is determined by the gap of this particular thing, which is basically the D. And this D is basically the gap between these two rings. And then you define the resonance frequency, and you need to derive it. Then we talked about different configurations of these. You can have a split ring resonator like this. You can have a ring resonator like this. So here the normal current flows, and here the displacement current flows. That is what basically happens in the capacitor. And then we talked about how to do it at optical frequencies, because optical frequencies are much higher than that of the RF frequencies. They go into a terahertz regime. They can be maybe 500 terahertz or 50 terahertz. They can be huge. And then we talked about certain systems. How do we confine the magnetic fields using certain pyramid type of structures? But these are layered structures of metal dielectric systems, or I should say metal, and you have a dielectric in between. So it's almost like a metal insulator, metal type of a structure that is going to give you the magnetic responses in these particular systems. And mostly these are used at near IR frequencies. Then we talked about lenses. We talked about perfect lenses, and what happens if you have, let's say, for example, a metamaterial to behave as a lens. That means you have something with a negative index. And how is it going to focus the light, which is coming from, let's say, an object placed at its focal point? Then we talked about its impedance mismatch, wherein if you have the characteristic impedance of the free space matches the impedance of the medium, then you would be having perfectly matched systems. And perfectly matched systems means the reflection almost tends to zero. That happens in electrical systems, optical systems, mechanical systems. That happens in most of the systems. And when the reflection falls to zero, the transmission becomes equivalent to one, and you have the wave which is basically going inside, and you have the perfect lens system created. That means what it does is that it amplifies the evanescent modes inside this. That is this basically part e to the power plus kappa d, which is basically the amplification of the evanescent mode. Okay, that means if you place some kind of this negative index material in close vicinity to a material where the wave is leaking, that can basically couple into this metamaterial, and it can get amplified inside the system. That is basically the phenomena of the perfect lens. So that is what I talked about. I talked about here this concept of acoustic impedance mismatch, which happens to be a universal concept in whether it's electrical, thermal, mechanical, optical systems, or whether it's any systems. These happen to be a universal concept because they are all related to the concept of the waves. So if you have incoming acoustic waves over on the water surface, let's say, then most of it is going to get reflected because the acoustic impedance mismatch is huge, where in the acoustic impedance there is given by the product of the density of the medium times the speed of sound in that particular system. So that is the phenomena used in the ultrasound, and that is what I basically showed here. That if you have a if you have ever done an ultrasound scan, you might know that they apply this particular gel over the belly. Let's say you have to do the ultrasonic scan, ultrasound scan of the belly. They apply this lotion in order for the acoustic impedance mismatch to be better, or to match the impedance of the media, so that you can get most of the waves inside it, and you can just capture it using the transducers, and then you can image it using certain image reconstruction techniques. Then we went into plasmonic metasurfaces. Plasmonic metasurfaces, we talked about how we can control the bending of the, let's say, electromagnetic waves. Here we talked about phase fronts, which is basically controlling of the controlling of the electromagnetic waves. So phase friend is the concept given by basically Huygens, and so these are just like the planes of the propagation of the electromagnetic wave. A single phase friend leads a primary phase friend leads to secondary phase friend, and that is how basically electromagnetic wave was understood in the classical optics terminology. And we talked about that if you can make a glass, let's say something like this, then you are going to have a you can slow down these phase friends in certain places. You can fasten these phase friends at certain locations, and that is how the lens also behaves. So you have the thinner regions on the top of the lens, you have the thicker regions in the middle. As a result, the phase friends slow down on the middle, and they fasten on the top of the system where it is thinner, and then you get the bending of these waves or the incoming optical light. So then we basically talk about, because of this gradient in the phase, because of the variation in the thickness of the system, you have something called as spatial phase. So this phase is basically gives you the generalized Snell's law, which can be written in terms of this particular thing. So the generalized Snell's law can be written because if you have a system wherein the two media N2 and N1 are separated by certain media where you have a phase gradient, it's a phase gradient in space, which is basically d phi over dx, where this is the x direction. Then you can write a generalized Snell's law in this form, where this is basically k naught, which is the inverse of the wave vector of the electromagnetic wave, and then you can determine then this particular phase vector, which is d phi over dx, is going to determine the how much bending can take place. Then if you can control this particular phase vector, the gradient in the phase, you can control basically you can steer the beam. Okay, that is what basically I wanted to talk about this concept. So that's why I referred here to an example or analogy of the phased array antennas, wherein I should say different antennas are combined, but different phases are given to these different antennas. Let's say this is given a phase of pi, 0.2 pi, so on and so forth. As a result, what happens is that you can steer the beam in certain directions. You can create constructive interferences in certain directions and destructive interference in other direction. Let's say the waves interfere in such a way that the most of the constructive interference happens in this direction. So you have technically steered the beam in this direction. So you can control the steering of the beam without actually moving the antenna. Okay, one way, if let's say there are certain patches of antennas present on this particular pencil. One way to, let's say, if I want to if I want to throw the wave on this angle, then one way to do this is that I can just turn the antenna like this. Okay, but here what we are talking about, the antenna looks like this. The antenna is just like this. What you are doing internally is that the emitted phases of the electromagnetic waves are different. That is automatically going to transmit the electromagnetic wave in this direction, in the direction I showed earlier. So that is the fascinating thing of this particular concept. And that is almost like I should say the similar concept, but here you are giving a spatial type of a phase because of the varying thickness. Then we talked about certain different topological materials, topological metamaterials, wherein you have the different variations in the topologies associated with the geometry of this particular system. And I had talked about here that this topology concept, the topology concept or the topological concept, there is something, the field called as topological electronics. A topological electronics field deals with how the electron behaves in certain geometrical configurations. And I showed you that, let's say, for example, why the phase gets associated with these. Let's say, for example, you have an arrow, and the arrow starts at a north pole, and it just traverses to this point on the sphere, and then it goes here, then it comes here. When it reaches here, you would automatically see, because of the curvature of this particular sphere, you have the direction of the arrow just like this. It is shifted as compared to the original direction. So it has acquired a phase. So that acquired phase is something called as geometric phase. And in terminology of these topologies, it's something called as Berry phase, and it's the name of the scientist. And this Berry phase has important implications in the electronics, particularly in topological electronics. And it's a very hot research area in even today. But this was discovered back in, I don't know, a couple of decades back. So it gives rise to a field, totally different field, which is basically called as topological electronics. You talked about geometric phases, and it is altogether I should say, amalgamation of advanced quantum mechanical concepts and complex integration. You have to do a lot of mathematics in understanding how the electrons basically behave in these different topologies. That is the basic fundamental notion of these topological electronic courses. And that was about it, I guess. And then we moved on to the questions, wherein questions were mostly based on these concepts which I discussed. Uh, so the concepts, the questions were quite simplified, I should say. And now what we are going to see today is the week 7. We're moving into the week 7. Okay, so we have the what we are going to study today is light emitting metamaterials, but these are active metamaterials. What do you mean by active is that they are, just give me a moment, they can amplify your signal. Instead of just having the absorption, they can now amplify the signal up to a certain value, just like your transistor does. If you have let's say a transistor, if you give in certain signal, you get the amplified signal by whatever the process you might be knowing, obviously. And then we talked about the optical gain, just like you have a gain in the electrical systems. We talk about radiative and non-radiative transitions in the, let's say, the atomic systems, or even in case of the diodes. We talked about the amplification, amplified emissions. We talk about the lasing thresholds, and we talk about how you miniaturize these optical amplifiers. That is what you call as nano-lasers. So basically, lasers, what you see, they are the optical amplifiers. These are the optical amplifiers. Because that is the fundamental thing what we're going to talk about in this session. So this session, because of the time limitation, what I'll try to do is that I have made certain notes and I'll try to explain it, and wherever it's required uh, I'll try to annotate certain things in these particular notes so that it becomes easier for you guys to understand. Otherwise, if you just want to understand, or if you want to just create a flow in your mind, then you can just refer to these notes, but I'll be annotating here and there so that you can get these particular concepts. Okay, so we'll try to understand it for maybe 40 to 45 minutes. We'll go through these notes which I had prepared, and then rest of the time we'll try to solve the questions. So most of the questions I could see are directly based on what I'll be talking about in this particular session. Now, in the first lecture, the we talk about the tunable and active metamaterials. Now, what is this active metamaterial? Is that if you have certain active material, or a, let's say if I talk about general active material, not a metamaterial, then it is something that if you have incoming electromagnetic wave which is lower in amplitude, then you get a amplified version of this uh, particular electromagnetic wave, amplified electromagnetic wave. And I'll try to mostly annotate using the red color, so you can follow it. I have not used the red color in these notes. Wherever I have used the red color, that would be an additional annotation over these notes. So just try to understand that. Now, what we talk about is that we talk about mostly the previous concepts which we talk about, that how we create the LC resonances in these. Let's say, for example, this is a split ring resonator, split ring configuration, what you call split ring configuration, where you have the capacitances and you have the inductances and you have the resonant frequency, which depends upon the capacitance and the inductance. How it depends upon, we have talked about it in the previous sessions. Now, how you can even control it, or how you can tune it, is that you can connect a varactor diode, which is almost like a something called as variable capacitor diode. And if the capacitance changes due to the change in the depletion region, then you have the change in the capacitance. That is what basically a varactor diode does. So if you have, let's say, a PN diode, if you talk about a PN diode, let's say this is P, this is N, you have positive immobile ions in the depletion region. So this is the width of the depletion region. So you know what happens in the forward bias, what happens in the reverse bias. This is just like a basic device physics. You talk about something called as depletion capacitance, and you talk about junction capacitance. They occur in forward bias and reverse bias regimes, and that means you have a charges which are basically present here, and this immobile region acts like a dielectric, and you have the capacitance associated with it even in reverse bias and also in forward bias. Now you can control this particular capacitance because the width of the depletion region changes. If you forward bias it, it reduces. The width of the depletion region reduces. If you reverse bias it, the width of the depletion region increases. And as a result, you can control this particular capacitance. And by controlling this capacitance, you can connect it to this particular system, which professor might have talked about. It's connected to the bottom of this particular split ring system. So you can control the resonances. Okay, that is one way to do it. And that is basically something called as LC resonance control, or controlling using the something called as varactor diodes. And by using it, you can basically form a very superficial filter, just like a tunable notch filter. A notch filter means it has a notch-like response at some particular frequency or particular wavelength, whatever you call it. That is basically what is meant by the notch filter. And you can basically tune it also, and you can shift that particular frequency response if you go on increasing the voltage. Because if you increase the voltage, you are increasing, let's say, the forward bias. You increase the forward bias, you are decreasing the depletion width. That means you are increasing the capacitance, and that is directly going to affect the response of the this particular split ring configuration. And that is going to, if you shift this particular frequency response of this particular varactor diode plus split ring configuration system. Now, if you have, let's say, for example, a phase change material. What do you mean by phase change system? Is let's say, for example, phase change system is, let's say, for example, uh, for example, a tuning mechanism. Let's say, for example, if you have a crystalline system and you heat it, and somehow it changed its phase, just like, for example, ice changed to water. But these can be brought back, and this is controlled by the temperature. You go on increasing the temperature, and here you go on reducing the temperature, and that is as simple as that. But what is going to happen is that here you change these bond lengths in these particular systems, and it has now turned into the amorphous system. That means uh, uh, the the order repetitive arrangement, or the order, has been completely destroyed. And what is going to happen is that it now changes its refractive index. Okay, because once the bond length changes, all of the things are going to change. You might have studied about this particular system, the the dipole oscillator the dipole oscillator model. What do you talk about it? Let's say, for example, if I stretch this particular spring, that is basically means uh, that would mean a lot of things. Let's say, for example, it would mean stretching the spring means the electron going far away from the nucleus. But what if you have a lot of nucleuses present, and you have the bonds between these nucleuses, which almost like acts like a spring, and now you are stretching these springs, that is going to all together change the response of these particular atoms towards the incoming electromagnetic light. And that is what basically changes the refractive index as well as the permittivity in these particular mediums, in these particular phase change materials. And another thing is something called liquid crystals. These have been around for a while. You might have heard about something called liquid crystal displays. They are also based on certain, let's say, for example, systems where if you have isotropic arrangement, then you can just apply certain voltage, or you can even apply temperature that can be shifted. You can shift the temperature and that is going to shift the, pardon me, that is going to change the refractive index due to the orientation change. Okay, of these particular, let's say, crystals formed inside this particular system. Another technique is something called as mechanical stretching. A mechanical stretching is literally stretching the material. Okay, let's say, for example, if you have this particular split ring system made on a substrate which is, let's say, something called as PDMS. It's a polymer, and it's stretchable. Stretchable. That means you can stretch it, it will come back to its original position. And that is what is that going to do? That is going to change the distances between these two. This distance is going to change, And you know, once this distance change, the capacitance change. If the capacitance change, the resonance frequency is going to change. That means you have achieved a tunability. Tuning, you have tuned the resonances of these particular splittering systems. Okay, so but this is, I should say, quite a slow process. Even this particular thing, because this is literally moving the atoms going here and there. Similarly, this is also a slow process. But what happens if you have a carrier injection? Let's say, for example, you have a certain system where you can inject the carriers. Let's say, for example, if you have a quantum well like this, if you somehow inject, let's say this is n equals to 1 of a quantum well, if you somehow inject electrons in this quantum well, the refractive index is going to change. And this will be fast because the electrons motion inside it is fast. Electrons are going to populate this region very fast. And what is going to happen basically is that you will have a fast change in the refractive index. But this is for a very short period of time because you know that they are going to recombine later on. So that is the fundamental notion of the carrier injection mechanism. And what process to use to for better controllability of these resonances, whether we should use carrier injection, whether we should use one should use mechanical stretching or let's say phase change materials or let's say varactor diode systems. It depends upon what we basically want from the system. And there are certain performance metrics which we want out from these tunable metasurfaces. The first one is modulation depth, that how much there is a change in reflectivity or the transmissivity through in the system. That how much the, let's say for example, the refractive index is changing, or let's say the permittivity is changing, by how much value it's changing. The another one is modulation speed, that means how fast it is changing. Obviously, if it is changing by, let's say, mechanical stretching, then it's going to be slow. It's going to be very slow. Instead, if it's going to be changed by, let's say, for example, the carrier injection, then it's going to be fast because the motion of the electrons is very fast. Then another metric is the energy consumed. Obviously, you want to consume as less energy as possible in tuning the resonances of these particular metasurfaces. So this should be less. We're talking about ideal metasurfaces. And obviously, the wavelength of operation is going to be important because you would see that not all the wavelengths are going to be tuned by these metamaterials. Let's say, for example, you stretch this particular metamaterial and you expect all of the wavelengths to get tuned as per the stretching, but that's not going to happen because the response is for the particular wavelength, it's for the particular frequency only. Okay, so the wavelength operation of the operational wavelength is going to be necessary. And if we, let's say, talk about, that means if we, for example, talk about smaller wavelengths, it's difficult to change the refractive index. That means if you have, let's say, UV, it's very difficult to change the refractive index. And as you go higher, let's say towards IR or far IR regions, it becomes easier to change the refractive index because most of these far IR or IR electromagnetic waves are also responsible for heating of the system as well. Okay, rather the heating is itself a form of IR radiation. So if something heats up, it's emitting IR. Okay, so that brings up a huge change in the refractive index. Instead of a simple UV, which is a very lower wavelength or a high frequency electromagnetic wave, it's very difficult to get the change in the refractive index for these shorter wavelength systems. That's why it's difficult to fabricate a blue. Even the blue LED was difficult to fabricate, and even the blue laser is difficult to fabricate. That's why a person who made this blue LED got a Nobel Prize. He was from I guess he's the that guy is from Japan. Nakamura, I guess his name is. Uh, and it's very difficult to work in this particular region. So he fabricated it using certain layers of, I don't know, it's a nitride based material, but he just worked on it for years and years, and in optimizing the I should say concentrations of I don't know, gallium nitride, gallium arsenide, and so on and so forth. So it's a very difficult thing to do. And again, if you are heating up the system and expecting the resonances to shift, that is going to be slow, because heating definitely means the motion of these either atoms. If we talk about metals, then it's electrons also responsible for heating because of the electronic specific heat. But if we talk about dielectrics or the semiconductors, then these are mostly the atomic oscillations or the vibrations that mostly give up the result in the flow of the heat in these particular dielectrics. So that's also a slow process. Now, what we talk about is the active metamaterials. The active metamaterials, you have the optical gain, and you talk about three processes. You talk about absorption, you talk about spontaneous emission, and you talk about stimulated emission. That means consider if you have a two-level system, N2 and N1, where N2 is the, let's say, the number of atoms in the higher level, N1 is the number of atoms in the lower level. Each is having energy E2 and E1. Then as per the Boltzmann statistics, as per the Boltzmann distribution, Boltzmann statistics, you can write the population as N2 over N1 to be exponentially decaying with the energy. As you go higher in energy, the population decays. Okay, you don't expect a lot of population to be present at the higher higher states. Let's say this is energy. So there are huge concentration of atoms at lower energy, but for the higher energy, there are only few atoms present. Even that applies for the electrons. Now, what is going to happen is that for this two-level system, you can write a rate equation simply to be the change in dn1 by dt to be equivalent to n1. That means the variation in the population in n1 is going to be proportional to that of this. And you have this function, which is basically a function of frequency, something called a spectral density, and it represents the number of photons. And there is one more coefficient attached here, which is basically something called Einstein B coefficient. And this derivation is very, very simple. You can just derive it using certain basic arguments, and it's given in all of the basic books. You can just go through it. That's not my goal because this is a very fundamental thing. So my goal is to make you understand what is basically the difference between these three. And you can just go through these equations again. And this is and what is going to happen in the absorption? Incoming electromagnetic wave comes, and the electron, let's say, or the atoms even, they absorb the incoming electromagnetic waves energy, and they go to the higher energy state and start populating the higher energy. But as you go higher and higher in energy, it again becomes difficult to populate these levels. Okay, just because naturally there's a tendency for these atoms or the electrons to come to the ground state. Now, how does that they come to the ground state? They come via the spontaneous emission, either spontaneous or stimulated. Spontaneous emission is the natural decay. It's the natural decay of the excited system to the lower ground state. So this is the ground state, this is the excited state. And you can similarly write a rate law. That means the rate of change of atoms in the excited state will be proportional to the number of atoms in the excited state. And you have a certain constant here, which gives you the probability of the spontaneous emission. This is actually a rate. So it has a units of 1 over time. Okay. That's why this particular site has units of, let's say, per centimeter cube second. So this is per centimeter cube. So this has to have a units of 1 by second. So this is almost like a rate. That's why this spontaneous emission happens. Let's say, for example, if you have electron here, you have hole electron you created an electron hole pair, and it naturally has a tendency to go to the lower energy state. This is ground state, this is excited state. It wants to recombine, and the time is given something called as recombination time. Let's not write it right. The tau is called as recombination time. Now it may so happen that if you have an electron here and a hole here, then this particular energy, which is the excess kinetic energy of the electrons, it will be given off first in the form of, let's say, phonons, and these are going to heat up the system. Then it will come here, then it can decay either non-radiatively or it can decay radiatively. It depends upon it also depends upon the band gap. So non-radiative decay mostly heats up the system. Again, So let's say if it emits, let's say, IR or far IR light, that's also going to heat up the system. But the radiative decay is the emission of the electromagnetic wave, emission of the light. Mostly we talk about it in visible region, and let's say, for example, it emits 400 to 700 nanometer wavelength. And now what happens basically, there's another process called as stimulated emission, which almost sounds like it does not sound logical to many, but it's very interesting phenomena. So what happens is that if you have a system wherein the upper states are highly populated, you bring in some kind of external perturbation, which is, let's say, you bring in some light that interacts with this excited system in such a way that it brings all of these atoms or electrons to the ground state. While doing so, it emits a photon almost as similar to that of the incoming photon. So whatever there is incoming photon, I mean, whatever is the behavior of the incoming photon, the same is the behavior of the outgoing photon. So if the one photon goes in, the two photons come out, because one is the photon that goes into it. That does not get absorbed. That just brings the excited system to the ground state, just perturbs it. How that happens, that's a quantum phenomena. You cannot understand it. It's not just like absorption. It's not like absorption that you have a photon coming in and that photon gets absorbed here, because that's not going to happen. If the electron absorbs this photon, then it is going to go higher in energy. But that does not happen. What happens is that the photon comes in, the electron goes to this state. Instead, you have this photon, plus there is one more photon which is emitted because of the radiative recombination. That means you have two photons. So you have one photon in, you have two photons out. That means you have increased intensity, because intensity depends upon number of photons. So you have intensity increased. If you have increased intensity, that means amplitude of electromagnetic wave is increased. And now how do you want to sustain it? You want to sustain it, and you want to put this particular entire thing inside certain system uh, which can sustain this particular effect of stimulated emission. That is what you do. You put this inside a cavity. And that is what I'm telling you, that the emitted photons have the same polarization, they have the same phases, same frequency of that of the incident photon. That is the essential part of it. And that is why the lasers are possible, because whenever the emitted electromagnetic waves are all in phase, they constructively interfere with each other and give rise to a huge amplitude with same polarization, and a beam is almost as focused as what you see in a laser. That's as simple as that. And for this system, again, you can write a rate equation, which where this is the rate equation given by a certain differential equation, which is the variation of the N2 population with respect to the time, depends upon the certain coefficient, which is B21 coefficient. Obviously, it was these coefficients were described first by Einstein, so they are also called as Einstein coefficients. So this gives the probability of stimulated emission. And now, what he did is that he applied the principle of detailed balance in order to evaluate the relation between A21 and B21. So, in doing so, he found out that the ratio of A21 over B21 is equivalent to this particular constant, which is 8 pi h omega cube c cube, sorry, nu cube. So, this is A21 over B21. That means for the higher frequency, if you go on increasing the frequency higher and higher, what is going to happen? That means if nu increases, A21 to B21 is going to increase. That means A21, this coefficient is going to increase, this coefficient. That means you will have spontaneous emission dominant in the system. That's what happens. That means in, let me just rub this. That means in, if you go go on increasing the frequency, that means, let's say you go from IR to UV. That means you increase the frequency. That means A21 over B21 factor goes on increasing. That means you have the more probability of spontaneous emission, then that means the spontaneous emission probability becomes huge than that of the spontaneous. Then you have the huge probability of the spontaneous emission than that of the stimulated emission. So that is why it is very difficult to make a UV laser even, because in those systems, just because of this rate equation, you have been able to evaluate that in the if you want to bring in the stimulated emission in certain material and you want that stimulated emission to be in UV region, that is very difficult compared to that if you want the stimulated emission in IR. That's why you see many of the lasers in IR region, 800, 1500, 2000, even there is 10 micrometer laser, which is basically a carbon dioxide laser that emits in almost 10 micrometers. But hardly you will see, it's very difficult to make a UV laser because for the UV, the absorption is huge. Even if you have, let's say, if you have a laser and if you have UV laser, if you just shine it in the normal this space, this particular space wherein the molecules of the air are present, the gas molecules, they are going to absorb the UV, and you won't be getting UV at even few, I should say, meters of the distance. So that is the worst part of making a UV laser and also working with the UV laser. That means if you have a UV laser and if it emits, let's say for example, a UV light, you're going to get a faster absorption of this UV as compared to if you have another laser that is emitting IR that is going to propagate to a huge distance. That is why most of the communication lasers you see they are working in 1500 nanometers. Communication lasers used in optical fibers, wherein the inside the optical fibers you use the total internal reflection phenomena, but those lasers are basically around 1550 nanometers. That is why for that, that's why the one of the reasons is because the absorption is less and the losses are less. If they use UV, then losses are going to be huge because UV is even absorbed by the air molecules or the atoms, and they are not going to propagate a longer distance. And that's why even inside to make a material, active material out of to make an active material that can cause the stimulated emission in UV, that is very challenging and difficult because the absorption is huge. That is what basically this says. The absorption is huge compared to that of the stimulated emission. Okay, so that's what I have written here. The spontaneous emission dominates mostly. Now, what basically happens is that if you talk about this particular spontaneous emission, to be honest, in actual sense, the spontaneous emission is almost like a stimulated emission. But the only difference is that in stimulated emission, you need some external stimulus to bring the higher energy states or the atoms or the electrons toward lower energy all simultaneously. But in spontaneous, it happens spontaneously by its own. That is what we had understood. But in actual sense, if when you go into quantum mechanics, it turns out that's not the case. Nothing in the universe just happens by its own. It turns out that the spontaneous emission basically happens because there's something called as quantum fluctuations. Quantum fluctuations. People also call it as vacuum fluctuations. So the concept of vacuum fluctuations is that you don't have a complete vacuum ever anywhere in the universe. There are always certain atoms or particles or even photons popping in and out of the system. You cannot get an absolute vacuum. So that's the concept of vacuum fluctuations. That is what you will talk about when you go into quantum optics and if you when you go into second quantization picture of quantizing an electromagnetic wave and you arrive at a picture of photon, then you will see that even at zeroth level you will get a photon mode. You will get a photonic particle. That is basically the photon exists in a vacuum state. You will get some certain acceptable values in a vacuum state, or in a I should say theoretical or philosophical sense. It actually means that pure or absolute vacuum is not possible anywhere in the universe. There are always certain quantum fluctuations or the certain particles popping in and out of a system anywhere at any point of time. And what those do, let's say certain atoms or certain photonic particles are popping in and out here. There are certain photonic modes present at the vacuum level as well because of these vacuum fluctuations. They interact with this atom or an electron in the excited state, and they bring it down. That means it is almost now like a stimulated emission, but it's brought about by vacuum fluctuations. So the spontaneous emission is a stimulated emission, but stimulated by the quantum fluctuations. That is the essential line, I should say. And it is it's a field of quantum mechanics, a deeper field of quantum mechanics to understand these. Maybe we'll talk about when we talk about the second quantization, canonical quantization, or going into the photonic picture, and how the light matter interaction takes place at quantum mechanical scale instead of using the classical dipole approximations or classical dipole picture. We will be talking about it in the next week, maybe next session. So then what else is important in this is now using this particular concept of stimulated emission, what we do is that we have formed it into a system where we can get a intense, sharp, amplified beam of light, which is almost like a optical amplification. So what you do is that you put this particular active material inside the cavity. The cavity is something which is surrounded by two reflecting surfaces. Okay, it's not necessarily mirrors. These are just reflecting surfaces. These can be just some some etched cuts, some semiconductors which are etched. Oh, and at the ends by using certain nanofabrication techniques. They can act like a mirror. So mirror here means something that is reflective. So mostly this is almost like 100% reflective, and this is like less than 100% reflective, so that you have active material, you have some photons coming in, one photon goes in, you have two photons coming out, then that gets reflected, that brings in, this almost like a chain reaction starts. So if you have one photon going in, you produce two photons, they give rise to four photons, they give rise to eight photons, so on and so forth. And once the population of photons reach to a certain threshold value, the intense beam comes out from this uh, particular site, and you get a lasing action. So that's why the cavity is essential. Okay, so this is the concept of the optical amplification, even how you amplify the optical signals. Now, even if you have, let's say, for example, you talk about the electronic amplifiers, you know that these are basically oscillators. And whenever you have oscillators, what do you amplify is basically the noise. So you have the noise, and that gets amplified. Okay, because it's a constructive feedback system, and that is what mostly happens in. Uh, you might have talked about Schmitt triggers or electronic oscillators that gives you oscillating frequencies at, let's say, for example, gigahertz range. How are they able to produce these oscillations? Because they amplify the noise that goes into the amplification, that goes through the feedback circuit, that goes to the feedback mechanism, and then it starts to amplify, and you get a pure sinusoidal oscillation. But that comes out from a pure noise, almost like from the thermal noise. That is almost, I should say, the noise here in these optical systems. What is the noise in optical systems? Noise in optical systems. The noise is basically spontaneous emission. So the spontaneous emission acts like a noise because you don't want spontaneous emission to happen. You just want stimulated emission to happen because spontaneous emission gives you a photon which is totally out of phase, out of polarization, and in some random direction. But the stimulated emission gives you uh, in phase, in polarization, and a directionality to the photons. And so what happens is that you need few things in order to do this lasing. First, you need some source, just like in a transistor, you need DC source. You need some energy source for amplification. Just like if you have a transistor, you connect some VDD here, which is basically the energy source, and then if you give a lower signal, you get a higher signal here. But where does the energy come from to amplify it? That comes basically from the source. So that's why you need some source in optical systems also. Let's say this source is some light source. Let's say this is called as pump. It brings the atoms to the higher energy state. And then you bring in some other perturbation, some light source, some light, again another light, and it brings these atoms down and you emit photons, which is basically in phase and polarization and frequency. So you have the lasing mechanism. And then you bring in this active system into a cavity and you sustain these oscillations and you get a huge amplitude. That's basically the fundamental of the optical amplification. Now it turns out it's not easy to get population inversion because nature does not support it so easily. That's why you don't see most of the systems to laze, but most of the systems undergo spontaneous emission. Even right now, the LEDs, which are basically giving the light, or the screens, the light coming out from it is a spontaneous emission. It's not a stimulated emission. Okay, otherwise your eyes would have been burning right now. Okay, so why is it difficult? Because it is difficult to sustain the excited state population in a system. Because if you want to sustain, let's say for example, you have 100 electrons in the upper level and 0 electrons in the lower level. So they will try to equalize the system. They will try to make it 50-50. They will try to equalize the system. Okay. And once they do so, they won't give rise to any of the photons. Even the incoming electromagnetic beam will just pass through it. And that is basically that's what happens in something called a saturable absorber. Saturable absorber. If you have let's say for example a population where there is the same number of population is in both the states, then the incoming electromagnetic wave just passes through it. Okay, it's almost like it's something called intensity based absorption. So absorption, if intensity goes increases, the absorption goes on increasing. That is almost something called intensity dependent absorption, and that is basically based on this particular principle. If you have equal populations in upper and lower states, you cannot absorb the electromagnetic wave. You cannot just reflect it. It just gets transmitted through the system. Now, what happens is that how you do it? You create three level system or four level system, or I should say higher level systems, and that basically gives rise to a population inversion in these optical systems. So what you do is that you have the ground state, you have the upper state, then you have the intermediate state. Okay, so you have the three levels. So the electron goes from this to higher energy, then it fastly decays to the lower energy. It's almost like a non-radiative decay, and it sometimes gives off heat as a heat that means in the form of a certain IR radiations. And this process is spontaneous, obviously, but it's fast. But then it accumulates in this particular level, intermediate level. And once it does so, then we bring in another source of light which perturbs it and brings the all of these electrons down to the ground state. And this is where stimulated emission happens. Stimulated emission. That means you want these electrons to be in this particular state for as long as possible. So this decay is slow. From let's say if this is state 1, this is state 2, this is state 3. So from 2 to 3, the decay is fast, and from 3 to 1, the decay is slow. Okay, so these are like long lifetime states. So now that is how the basically lasing happens. Now you can have there are four level systems, even higher level systems that are basically responsible for lasing as well. And people have been working in it for a longer period of time now. But as an electronics and electrical engineers, we are interested in semiconductors and we want to make everything out from a semiconductor. So that's why people are working on semiconductor lasers as well. And because you know that you can separate the electrons and holes in these systems, so you can make them lathes. But it's very difficult from the fabrication point of view, but people do it. And if you can just separate using certain heterostructures with varying band gaps, you can create electrons and hole population in such a way that it gives rise to a stimulated emission. Okay, that is fundamental of the diode lasers. Then there are something called as quantum cascade lasers. There are vertical cavity surface emitting lasers, and these quantum cascade lasers are again the certain quantum wells. They are separated by certain widths, certain values, and the electron goes from this energy state to this energy state, and while it does so, it emits a photon. Then there's a cascade of photons coming out from all of these wells, and there's a cascade reaction happening. So that is basically the fundamental of something called as quantum cascade laser. I'm just giving you a basic overview of what happens. So now, what do you want is that you want to miniaturize these entire systems. Just give me a moment. So what you want to do, why do you want to miniaturize? Because you want to make them on chip. You want to make them on chip. Why? Because you want to process the data on chip. Just like you have a, let's say, uh, a silicon chip, electronic chip that is very small now. You want to make the similar kind of arrangement for the photonic chips so that everything can fit on a miniaturized device. That means you want let's say for example a laser source, you want the waveguides, you want the demuxes or the multiplier or the demuxes or uh, I should say detectors on the other side, so that every processing from the generation to the guiding to the detection, that is going to happen on a single smaller miniaturized system, which is basically on chip or miniaturized photonic circuits. And it will almost it will mimic the electronic chips once it happens. It is still in progress. People are working on it. Many have achieved this particular phenomenal, I should say, photonic integrated circuits. So now the other details, you know that if you minimize this, their efficiency is going to be increased. It's going to be much way faster because if you have miniaturized it, now the light has a less distance to travel and it's going to travel at a huge speed and it's going to travel very faster. Now, what are the other things? I guess these are other things which are mostly theoretically described by the professor. You can just go through it. Hmm. Yeah, so I'll discuss about this particular thing. So the concept is that how do you improve the optical gain now? Now you have a let's say for example, material, whether it's an active material, whether it's a semiconductor, it can be anything. Now how do you improve gain? What can you do to improve the gain? Okay, give me a moment. So one way to do is that to there are certain ways to do it. One way is via the strain. I'll talk about it each and everything. One way is to dope it. Another way is surface passivation, strain I talked about. So everything what it does is that, let's say for example, if we talk about strain, it's going to play with the band structure, play with the band structure. You have, let's say for example, tensile strain, you have compressive strain, and that plays with the curvature of the band structure. And once you play with it, you play with the effective masses, you play with the energies of the electrons, and you shift the electrons' energy. That is that is what basically does is that basically shifts these Fermi levels as well. And once these Fermi levels shift, you can have change in the gain response. Even the absorption coefficient is going to change. So that is the simplest way to do it. But obviously there is something called a strain engineering. People have been trying to do it. And what basically happens is now, let's say for example, if you have a band structure like this, I have actually done a DFT calculation wherein if you give us tensile strain, the band structure basically shifts like this. I'm talking for the electrons right here, not the holes. That means this is E and this is K and this is for the electrons. I'm showing the conduction band only. So if you give the tensile strain, this is it shifts like this. But if you give a compressive strain, it shifts like no, sorry. So blue one is for the this is for the compressive strain, and if you give tensile, it shifts like this. This can be basically understood by certain density functional theory calculations, wherein you can calculate the band structure of any of the semiconductor or even the metal, and then you can give a small strain to the atoms, recompute the band structure, and when you see that the Fermi even the Fermi level shifts, and there's a shift in the band structure. So now there is again something called as surface states, which are basically certain states present at the surface of even the semiconductors have it. So if you have let's say this is a semiconductor where this is the Z direction, this is the growth direction, you know that near the surface there are a lot of states available. Okay, and these can be donor types, these can be acceptor types, and sometimes because of this there is a bending near the surface. It's basically called as surface bending. Okay, so surface states can be present here, even in the band gap. Okay, what it affects is that it affects something called as surface recombination velocity. It affects the motion of these electrons over the surface. So once that happens, because these are like traps. So if an electron wants to move near the surface, they get trapped and they get slowed down. And once they get slowed down, they altogether all of the responses change. Even this is a huge implications in electronic devices as well. And it impacts the mobility of the electrons because wherever you find the trap, the electron gets trapped there, it gets slowed down, and it has a huge implication in the carrier dynamics. And once it happens, obviously now it's not going to absorb the same electromagnetic energy. It's going to absorb in a different region. It's going to behave differently to the incoming light. So altogether, these are the, I should say, ways to modify the responses. And another way is doping. Obviously, p-type doping is going to you are going to have a more whole concentration compared to that of the electrons concentration. And because of the variation in the curvature of the valence band compared to that of the conduction band, you have the Fermi level inside the conduction band and not the valence band. So once the Fermi level gets separated, these are basically quasi-Fermi levels. So that means we are talking about a highly non-equilibrium situation, wherein you have electron hole pairs created, let's say because of the incoming light. So you have the quasi-Fermi levels, and because of the different curvature and the different effective masses and different density of the states as well, you see the Fermi level for the electrons is inside the conduction band. For the holes, it's not inside the uh, I should say valence band. So what you try to do is that then you try to dope it heavily, p-type dope. What's going to do that? That's going to shift this Fermi level towards the valence band. It's going to go into the valence band then. And why is it important? Because the gain or the absorption depends upon the difference in the Fermi level. So if you can tune the differences in the Fermi level, you can tune the responses and you can tune the gain as well. So that's as simple as that. Now, what are we going to see? We talked about the Hermitian system in the lecture 5. I'm not going to go into the details. You can just look at the video because it's a very short video. Professor has tried to explain what are the Hermitian and the non-Hermitian systems. And we are going to deal with it when we go into the quantum mechanical aspects in the next week. Okay, so let's talk about the questions here. Or do we have questions? Yeah. So if we talk about the questions, the essential figure of merit for the to evaluate the performance of a tunable metasurfaces. What are the essential figures of merit? I talked about the modulation strength, speed, and the size of the metasurface. They're going to be important because this modulation strength represents how much is the change in, let's say, reflectivity or the transmissivity, or the change in the, let's say, permittivity or the refractive index compared to that of the original. So if the change is large, then the modulation strength is going to be large. Modulation speed is how fast you can change the, let's say, refractive index or the permittivity. That means how fast these particular things are changing. You want this to be as fast as possible for the fast response of the material. And the size of metasurface is going to be obviously essential because you don't want them to be small, you want them to be miniaturized. Because that also, I should say, determines the resonance frequency of this particular system. And power budget is also important because it represents the energy consumption. That means how much you are going to consume in order to tune the resonances of these metasurfaces. Let's say you have a certain surface and you are giving in, let's say, 1 microjoules to phase change it. Okay, but on the other hand, you are giving 1 nanojoule to the other system to phase change it. Then obviously this is going to be much more efficient than compared to that of this. So that is basically what they mean by power budget. So this is a multiple select answer type, and I hope these are the answers of the questions of this question. So the primary mechanism for achieving dynamic permittivity modulation using the phase change material. So dynamic permittivity modulation is so change in the epsilon, or rather change that is going to change the refractive index using the phase change material. So what is basically the theory? That the rearrangement of the constituent atoms on application of voltage bias, thereby changing the change from amorphous to crystalline. Definitely we change it from this amorphous to crystalline, and not the excess carrier generation, because this is the fundamental for the carrier injection mechanism. Injection of carriers, not again physical. This is basically the mechanical modulation. So now we have option this and option this. Now we have to see what is basically the fundamental. So rearrangement of constituent atoms on the application of thermal energy, thereby change of the state from amorphous to crystalline. So I guess this should be on the application of the voltage bias. You can change the state from amorphous to crystalline. So if you have certain materials, let's say these are the atoms, then you can basically apply certain voltages, and it can result in the phase change of this particular system. Let's say this goes like, let's say for example, this goes like this. And because of this, there will be a modulation of the permittivity as well as the refractive index. It's as simple as that. Application of thermal energy. Okay, but phasing can be brought even by thermal energy. I don't exactly understand what they mean. Whether there's a particular definition of this that it can happen in, I should say, under the voltage or thermal. Yeah, let me just check it. But I guess this should be the answer of this question. Some of the prominent permittivity tuning mechanisms are the correct order of switching speeds. Okay, so we have to choose the correct order of these modulation permittivity changing mechanisms on the basis of how fast, which one changes fast. So I talked about the mechanical actuation is going to be a lot slower because this is mechanically, you are just tuning it, you are just activating it mechanically, either by stress or the some mechanical thing. So it's going to be slowest. The fastest is going to be this one, photocarrier excitation, because it involves electrons, it involves holes, it involves the radiative decay and the non-radiative decays and the electron hole pair recombination. That's going to be very faster. And the phase change materials is also going to be slower. So I guess this should be faster compared to that of this, compared to that of the mechanical. And that means this the answer is the phase change, the photo excitation is greater than PCM is greater than mechanical acceleration. Yes, this is the answer of this question. So this is the order of switching speeds. That means in case of how fast, let's say for example, you have a system, and if you have a photo excitation mechanism, then the permittivity is going to switch faster rather than if you have a mechanical system, then you have to stretch it, and this stretching of bonds and atoms, then reconfiguring it back to its original position is going to be a lot slower. Okay, compared to that of what happens in a phase change material, that's also slower, but it is faster compared to that of the mechanical one. Okay, because the phase change happens because of either it can happen because of the voltage, it can happen because of the temperature, and all other perturbations can also result in the phase change. Okay, so now there is similar question, but we have to give the correct order of modulation depths. Modulation depths means how much is the change in the refractive index, or how much is the magnitude of change in permittivity or the reflectivity, or let's say the transmissivity, how much is the change happening in these particular systems. So if the correct order of modulation depths is going to be achieved, then we have to see that the prominent permittivity or tuning mechanisms. What is the prominent permittivity tuning mechanisms? In which of these is the modulation depths higher? So obviously, if you are mechanically stretching it, then you are bringing in a lot of change in the refractive index and the permittivity compared to that of the photocarrier excitation. It brings in a smaller chains. Okay, so it's almost the inverse of this because faster the response, slower is the change. Slower the response, the fast the I should say slower the response, huge is the modulation depth. So it will be I should say this particular thing. The mechanical actuation should bring in a lot huge change in the refractive index and permittivity compared to that of the phase change compared to that of the photo excitation. Okay, okay, that's clear. Now, given below are the calculated gain spectra of the gallium arsenide nanopillars with varying radii. So you have the gain spectra of nanopillars, and the radii have been varied. We have to choose the correct statement from the following. First, the radius is reducing in this direction. So let's say this is 25 nanometers, this is 75, this is 225. And you see the gain is reducing. So the optical gain reduces with reducing radii. That is what we can see. This is the gain, and this is getting reduced. And another is surface recombination aggravates with reducing gain. That's what I talked about in the surface recombination. And lasing is difficult to achieve with smaller nanopillars. Why? Because the gain is reduced. And another reason is because interaction area in the smaller nanopillars is smaller, so you have difficulty in lasing. So you have difficult to get the stimulated emission. Okay, give me a moment. I'll be back. Okay, so what is going to happen is that you will be having a stronger probability of stimulated emission or lasing in case of the larger nanopillars. One reason that can be also seen because the gain is larger here in the larger nanopillar. That's what you want in case of the amplification process to happen. Now here, this is what I talked about in a detail in the previous slides. What basically this shows is that we have to match the phenomena with the absorption, spontaneous emission, stimulated emission, and trap-assisted recombination. So this trap-assisted recombination I didn't talk about, I'll talk about here, but the other processes we talked about. So let's say if we talk about A, then what's going to happen is that it's basically showing the electrons recombining back with the holes and emitting a photon, and it's happening by its own. So it should be spontaneous emission. The B, let's talk about C first. What's happening in C that electrons are going to the higher excitation state. It's absorbing a photon, so it's basically absorption. And here the incoming photon is coming. It's bringing the electrons back to the ground state and emitting two photons. So this is stimulated emission. Okay, so that's what I talked about. And the B1 is basically what is basically happening. This is something called as trap assisted recombination, and it's also something called as there are a lot of phenomena, processes of the recombination. Another one is something called Auger recombination, the SRH recombination. This is basically the form of that. What happens here is basically electrons and electrons kind of electron goes to a intermediate trap state. Here's a trap present. It might be some energy level. It goes here and then recombines back with the holes. Another process that happens is basically if an electron and electron interact in such a way that whenever they come in close vicinity to each other, one of the electron goes down, another electron goes up. This is almost something called as Auger recombination. There are a lot of recombination mechanisms. Okay, here you can see that the up arrow is basically showing here the creation of it's almost like a hole is created. Okay, but it might sound confusing, but this is what basically happens. And I don't want to go into the details because this is a part of device physics. Then you can basically you can look at the process of SRH recombination process. You can look at Auger recombination processes. Then if you want to understand these trap assisted recombinations. Okay, so now what? So the A is this is uh, spontaneous emission. So this is A, B. This is B. This is C, this is D. So for the one, it is C. Okay, so one, it is C. So two, it is A. Three, it is B, and four, it is no, it's D, and here is B. So this should be the correct order of the matching. And here again, we talked about the if you have a two-level system where this is N2, this is N1. So consider an atom, the rate equation for spontaneous emission. We need to write the rate equation for the spontaneous emission. That means the electron is, let's say, coming from upper state to the ground state and it's emitting a photon. That means we will be talking about a rate of N2 over dt, dN2 over dt. So that is obviously given by this particular relation with a negative sign. This basically indicates that as N2 goes on, that means this rate goes on reducing as N2 goes on increasing. Sorry, let me just rub it. Okay, so what it basically says, what is happening? So what it basically says is that the dn2 over dt is proportional to minus times n2. So this is a simple rate equation. That means if this goes on reducing, this goes on basically in the opposite fashion. So that means if you have a lot of atoms here, if that the number of atoms start to reduce, and obviously the spontaneous emission is going to go lower. Okay, this is just like a rate law. Even the radioactive decay follows this law, and a lot of other processes follow these type of equations. And the radiative lifetime of an atom in an excited state. So there's an excited state. So the atom is here. So it is emitting radiatively, and the radiative lifetime is 1 nanoseconds. This is 1 nanoseconds. The time in which the carrier density in the excited state reduces to 1 by 2 times the initial value. So you know that if there is a, so as per this rate law, dn2 divided by dt equals to minus a 2 to 1 n2. So you can basically solve it. You can write dn2 to be equivalent to minus a to 1 dt divided by n2, and you get, what do you get? Ln of n2, oops, minus a to 1 t. You get n2 to be equivalent to some n naught. This is basically n2 over, when you just apply the integration and you apply the limits, you get n2 over some n naught to be equivalent to e to the power minus a to 1 into t. So this is the exact form you get. That means there's an exponential dependence on the time. So it's almost like this. This is n2 of t. This is t. So basically at 1 by e value, at something called as the radiative lifetime, which is basically the tau r value, the concentration falls to 1 by e value. And it is basically talking about what happens at 1 by e square. So 1 by e square will be lower than this. So the time in which the carrier density excited state reduces to 1 by e square. So we need to find this time tau. One of the ways to solve this, because this A21 is basically A21 is basically 1 by tau. It has to be some time inverse of the time in order for the dimensions to vanish in the power of the exponential. So one way is to solve this. Just put it whatever is given. And another way is that you know that the radiative lifetime is defined as the time at which the concentration falls to 1 by E. So the time at which the concentration falls to 1 by E square will be tau r plus tau r. So that is how you will get 1 by E square. Okay. That means if the tau r is 1 nanosecond, so 1 nanosecond plus 1 nanosecond is 2 nanoseconds. That's as simple as that. So if at tau r the concentration was 1 by E, then at tau equals to 2 tau r, the concentration will be 1 by E square. So it will be 2 nanoseconds. Or you can go by the conventional way, just solve this. You will get the same thing. So now I talked about because the A21 to B21 ratio is dependent on frequency cube. Okay, when I talked about the processes in the previous slides. So because of that, it is really difficult to build a blue laser compared to that of the red laser. Because in the blue laser, in the blue spectrum, you will have more dominated spontaneous emissions. And that is what the reasoning is. Spontaneous emission becomes stronger with decreasing wavelength. That's what is saying, that A21 over B21 is approximately equivalent to 1 by lambda cube. So if lambda goes on reducing, this overall factor goes on increasing. That means A21 becomes huge for a smaller wavelengths. So S1 is 2 and S2 is 2 and S2 is the correct explanation of S1. This comes from just the ratio of Einstein coefficients. Einstein coefficients. Okay, what else? The primary mechanism for achieving dynamic permittivity modulation using indium tin oxide is rearrangement of the constituent atoms on the application of voltage bias, thereby changing the state from amorphous to crystalline. It's not this, it's not this, it's not this. Indium tin oxide is again almost like a semiconductor. So you bring in the arrangement by using the voltage bias. Okay, so for this, the answer is voltage bias. But for the previous one, I believe the answer is the thermal modulation. Here, thermal energy. Okay, so this one. But for the ITO, you just apply the voltage and then you bring in the change from amorphous to crystalline. Okay, that should be the answer of this question. And I've talked about these uh, mechanisms of the phase changes inside this particular different materials. Okay, so I guess we are done with the today's session. And what I try to do is that I try to cover I try to recap from the previous section, which is week 6, because there was some audio issue, and then I went to explain the week 7. And in the next week, we are going to talk about two-level systems. Two-level systems. We are going to talk about Rabi oscillations. I guess we are going to talk about atom or photon cavity interactions, photon in a cavity. We're going to talk about all of that. Okay. And that's it for today's session. I'm stopping this session here. Okay. Thank you.